One of the universe's most wanted particles is still missing. This is the monopole problem, a cosmic mystery centered on the baffling absence of magnetic monopoles. Their disappearance challenges our core ideas about physics and the Big Bang itself. By the end of this, you will understand how this single missing piece could unlock a technological revolution, from limitless energy to computers of unimaginable power. Why does our best science insist these particles must be out there, yet our universe appears completely empty of them? How could finding one rewrite the rules of reality? What do you think is hiding in the vast emptiness of space? Every magnet you have ever held tells a lie. Break a bar magnet in half, and you do not get an isolated north and an isolated south. Instead, you create two new, smaller magnets, each with its own pair of poles. This is the world as we know it, a universe of magnetic dipoles. Yet our most fundamental theories of physics scream that this should not be the whole story. To see why, look at electricity. We take it for granted that positive and negative electric charges can exist completely independently. You can have a single proton with a positive charge utterly alone, or an electron with a negative one. The symmetry is perfect and undeniable. So where is the magnetic equivalent? A magnetic monopole would be exactly that, a solitary, fundamental particle that carries only a north magnetic charge or only a south magnetic charge. It would be the magnetic counterpart to the electric charge, a missing piece of a cosmic symmetry that feels almost too elegant not to be true. Finding one would be as profound as discovering that after a lifetime of only seeing positive and negative charges glued together, you could suddenly hold a particle that was pure, unadulterated positive electricity all by itself. This is not just a trivial oversight in nature's design. The shocking absence of these particles, which our best math insists must have been created in unimaginable numbers at the birth of the universe, is the very heart of the monopole problem. Why would the cosmos so clearly establish a rule for electricity, only to seemingly break it for magnetism? The conviction that monopoles must be real is not based on a whim. It comes from one of the most brilliant minds in physics, Paul Dirac. In 1931, Dirac made a stunning theoretical connection. He showed that the mere existence of a single magnetic monopole anywhere in the cosmos would automatically explain one of nature's deepest mysteries, the quantization of electric charge. What does that mean? Look at the world around you. Every electric charge you have ever encountered, from the shock of static electricity to the current in your walls, comes in discrete, indivisible packets. The charge of an electron is a fundamental unit, and every other charge is a whole number multiple of it. You never find an object with half the charge of an electron, or 1.7 times the charge. Why is that? Why is charge not a smooth, continuous quantity like the flow of water? Dirac's mathematics revealed an answer of breathtaking elegance. If even one solitary magnetic monopole existed, its magnetic charge would force electric charges to be quantized. The presence of that single north or south pole would create an invisible condition in the fabric of space, a rule that demands electric charges come only in those specific whole number packages. Think of it like a cosmic lock and key. The monopole is the unique key that, by merely existing, locks electric charge into its discrete steps. This is not a minor detail. It is a profound and necessary link between two fundamental forces, electromagnetism and quantum theory. Dirac's work transformed the monopole from a curious possibility into a vital missing component of a unified physical reality. Its predicted existence is a consequence of our most trusted equations, a ghost in the machine of the universe that we have yet to see. Dirac planted the seed, but modern physics has made the problem infinitely more urgent. Our quest to unify the fundamental forces has led to grand unified theories, ambitious frameworks that aim to describe the electromagnetic, weak, and strong nuclear forces as different faces of a single primordial superforce. These are not wild guesses, they are the logical next step beyond our incredibly successful standard model of particle physics, and they come with a dramatic, unavoidable prediction. In the first fleeting moments after the Big Bang, when the universe was an indescribably hot and dense soup of energy, a phase transition occurred as it expanded and cooled. Think of it like water freezing into ice. As the universe cooled, the perfect symmetry of the unified force was broken, crystallizing into the distinct forces we see today. But just as freezing water can trap air bubbles or form cracks, this cosmic freezing was not perfectly smooth. In the fabric of space-time itself, topological defects formed. These are like knots in a rope or cracks in ice, stable imperfections that the smoothing process could not erase. Magnetic monopoles are predicted to be one such defect. They are the cosmic knots that got tied during the universe's rapid change of state and simply could not be undone. According to these grand theories, these knots should have been produced in staggering numbers, a flood of monopoles saturating the cosmos. The math suggests there should be so many that they would be as common as protons, making them literally impossible to miss in our modern universe. Their overwhelming absence is not just a puzzle, it is a direct confrontation with our most profound ideas about how everything began. So the universe should be absolutely swarming with them. The calculations from grand unified theories are not subtle. They paint a picture of a primordial cosmos where magnetic monopoles were forged in overwhelming numbers, a relic population so dense that their collective mass would have dramatically reshaped the destiny of everything. These are not particles that would be hiding in the background. If the theories are right, monopoles should be so common that they would outweigh all the stars and galaxies we see. Their gravitational pull would have been so immense that it could have literally collapsed the universe back in on itself long before any stars or planets ever had a chance to form. The expansion we observe today, with galaxies flying apart, might never have happened. The cosmos would have been a very different and much shorter story. Yet when we look out with our most powerful telescopes and listen with our most sensitive detectors, we find nothing. The silence is deafening. After decades of searching, from deep underground laboratories shielded from cosmic rays to vast arrays scanning the heavens, the tally of confirmed magnetic monopoles remains at a perfect, unyielding zero. This is not a small oversight. It is a gaping chasm between our most profound theoretical predictions and the stark, empty reality we actually observe. How can our universe look the way it does if the foundational event of the Big Bang produced a flood of particles that should have made this universe impossible? That is the monopole problem in its most frustrating form, a cosmic paradox that demands a solution. The paradox seemed absolute, a dead end for our grandest theories. Yet physics thrives on such crises, and from this one emerged a solution of such breathtaking scope that it reshaped our entire picture of the cosmos. The answer is cosmic inflation. Picture the universe in its first fleeting moments, a domain of unimaginable energy where those monopoles were forming in a dense, hot soup. Then something extraordinary happened. A peculiar field of energy, dubbed the inflaton field, suddenly dominated everything. It triggered a phase of exponential expansion, a growth spurt so violent and rapid it defies all everyday comparison. In a span of time almost too short to conceive, a duration far less than the blink of an eye, the universe doubled in size and then doubled again and again, over and over. It was not a gentle swelling, but a runaway stretching of the very fabric of space-time itself. What does this have to do with our missing monopoles? Think of a drop of ink falling into a vast, calm ocean. The ink spreads out, its color fading until it becomes utterly undetectable. Now, replace that single drop with an entire ocean of ink, and then inflate the ocean to a size larger than the entire observable universe. This is what inflation did to the primordial monopoles. That once incredibly dense population was stretched so thin, diluted across such an immense volume that their average density plummeted to nearly zero. The cosmic rug was pulled out from under them at a speed faster than light, effectively sweeping them out of our observable sight. The handful that might remain in our entire cosmic neighborhood would be so incredibly rare that finding one would be like searching for a single, specific grain of sand on all the beaches of Earth. Inflation did not destroy the monopoles, it simply hid them on a scale so vast we cannot see them. This elegant idea does more than just solve the monopole problem, it also answers two other profound puzzles. Why does the universe appear so uniform in every direction we look? Because inflation stretched a tiny, homogeneous patch into our entire visible cosmos. And why is the geometry of space so flat? Because inflation blew up the universe like a balloon to such an enormous size that any local curvature, like the surface of the Earth seeming flat to a person standing on it, becomes imperceptible. Inflation is the cosmic fixer-upper, patching multiple fundamental problems with one grand transformative event. It turned a catastrophic prediction into a manageable absence, saving our best theories from their own success. This decades-long silence has not meant a lack of trying. The hunt for magnetic monopoles is a testament to human ingenuity, a global effort that has stretched from the depths of space to the heart of ancient rocks. Since we cannot see them directly, scientists have become cosmic detectives, looking for the faintest traces these phantom particles might have left behind. One major line of inquiry looks out at the largest structures we can see, galaxies and galaxy clusters. These vast islands of stars are threaded with immense magnetic fields. Theoretically, a population of magnetic monopoles moving through these fields would leave a distinct fingerprint, a subtle effect on the field's strength and structure as they carried their isolated north or south charge along. It is like trying to deduce the presence of a single, unique fish by studying the overall currents in an entire ocean. So far, the oceans of deep space have shown no such telltale ripple. Another ingenious method relies on a dramatic prediction from some grand unified theories. A magnetic monopole could act as a catalyst, a subatomic meeting point that dramatically speeds up a process that is otherwise incredibly slow, the decay of a proton. In a tank of pure water surrounded by sensitive light detectors, physicists watch and wait. If a monopole were to pass through, it could trigger a chain reaction of proton decays, creating a flash of light with a very specific signature. These massive underground experiments, shielded from other cosmic interference, have watched for years. They have seen nothing. Perhaps the most poetic search looks not forward but backward, using the Earth itself as a historical record. Deep within the planet's crust, in minerals like ancient mica, crystals have lain undisturbed for millions, even billions of years. Their atomic lattices are perfect frozen diaries. The passage of a heavy, highly charged particle like a monopole would have left a permanent scar, a trail of damage through the crystal that would be visible under a microscope. Researchers have carefully split these ancient rocks, searching for etchings left by a cosmic visitor in the distant past. They have found trails from other heavy nuclei, but none that match the unique, devastating signature a monopole would carry. Every method, from the galactic to the geologic, has returned the same result, a profound and puzzling emptiness. The silence from the cosmos forced scientists to bring the hunt back home, to our own planet and into our most advanced machines. Here, the search becomes a matter of extreme engineering and sheer force. If the universe is not giving up its monopoles naturally, perhaps we can create them ourselves. This is the promise of particle accelerators like the Large Hadron Collider. By smashing protons together at velocities incredibly close to the speed of light, these colossal machines recreate, for a microscopic instant, the conditions of energy and density that existed just after the Big Bang. It is a brute force attempt to shock the vacuum of space into producing a particle that theory says should have been common long ago. The collisions are so violent they can momentarily unlock the symmetries of the primordial universe, potentially allowing a magnetic monopole to flash into existence. Yet, despite reaching energies once thought to be a sure threshold for their creation, the detectors surrounding these collision points have recorded nothing. No signature, no trail, no monopole. Other experiments take a far more delicate approach, listening for a whisper instead of trying to shout one into being. These rely on a principle from quantum mechanics called flux quantization. In a superconducting loop, a ring of material cooled to near absolute zero where electricity flows without resistance, the magnetic field passing through the center is locked into discrete quantized units. It can only increase or decrease in these specific whole number steps. Now imagine a single magnetic monopole, a solitary north pole, drifting through such a loop. Its very presence would represent a fundamental unit of magnetic charge, instantly changing the flux in the loop by exactly 1 quantum. This would create a detectable jump in the current, an electrical signal as clear and unambiguous as a single chime from a bell. Experiments using incredibly sensitive devices known as squid have been running for years, their superconducting loops acting as silent sentinels, waiting for that 1 in a trillion event. They are so sensitive they could detect the magnetic field of a human brain from miles away, yet they have never registered that definitive, singular click. The sheer ingenuity and power of these methods is staggering. We are trying to manufacture a piece of the Big Bang in underground tunnels and listening for the footsteps of a ghost with instruments of unimaginable precision. The fact that both approaches, from the violently energetic to the exquisitely quiet, have consistently found nothing is a result in itself. It tells us that if monopoles exist, they are either far more massive than our best estimates, placing them forever beyond the reach of our colliders, or they are so phenomenally rare that our entire planet might see one pass through only once in a million years. This relentless global hunt has not found the particle, but it has meticulously mapped the territory of its absence, narrowing the possibilities and deepening the mystery with every empty result. This hunt for the unseen has an apex predator, an experiment built with one singular, focused purpose. Its name is Monopole, the monopole and exotics detector at the Large Hadron Collider. While other detectors are complex, multi-layered marvels designed to track a zoo of known particles, Monopole is a specialist, a silent trap waiting for one specific hypothetical prize. Its design is elegantly simple and brutally effective, tailored to catch a particle unlike any other. At its heart are stacks of plastic sheets, similar to the material used in old-fashioned camera film. These are not electronic sensors, they are passive nuclear track detectors. When a heavily ionizing particle like a magnetic monopole tears through this plastic, it does not just pass through. It acts like a microscopic cannonball, blasting a trail of permanent damage through the plastic's molecular structure. The particle carves its own signature directly into the material, a fossil track that remains long after the particle itself is gone. These plastic stacks are then carefully removed and bathed in a chemical etchant, which slowly eats away at the damaged trails, enlarging them into microscopic pits that can be seen and analyzed under a microscope. The size and shape of these pits tell a story, revealing the mass and charge of the particle that made them. But Monopole has a second, even more audacious trick. Surrounding the plastic detectors are large volumes of pure aluminum, a metal chosen for its unique atomic properties. The idea here is not just to detect a monopole, but to capture it. If a magnetic monopole is created in a collision and passes through this aluminum trap, its immense magnetic charge could theoretically bind it to the atomic lattice of the metal, literally getting stuck inside the block. It is the ultimate cosmic flight trap. After a period of collecting data, these aluminum volumes would be carefully removed and transported to a specialized laboratory. There, scientists would use extremely sensitive instruments to scan the metal, searching for the distinct magnetic signature of a single trapped monopole. Think of it as trying to catch a ghost by leaving out a box it cannot escape from. Monople is positioned like a sentinel around one of the LHC's main collision points, a strategic location bathed in the aftermath of the universe's most violent artificial explosions. It sits there, patient and unblinking, as billions of proton collisions erupt around it, sifting through the cosmic debris for that one in a quadrillion event, for the track or the trapped prize that would rewrite physics forever. It is a monument to our stubborn refusal to let this mystery go unsolved. That single perfect signal arrived on Valentine's Day, 1982. In a laboratory at Stanford University, physicist Blas Cabrera observed a reading from his superconducting loop that sent a jolt through the world of physics. The data spike was clean, sharp, and exactly matched the predicted signature of a magnetic monopole. It was as if a ghost had finally rung the bell, one clear, resonant chime that seemed to answer a 50-year-old question. The news spread like wildfire, a potential discovery of monumental importance. Yet that solitary signal was all there ever was. No other experiment ever saw it again. Cabrera himself spent years trying to replicate the result, refining his apparatus, but the Valentine's Day monopole never returned. It became the most famous non-discovery in modern physics, a tantalizing ghost that underscored just how difficult this hunt truly is. It was not the only near miss. Over the decades, other claims have surfaced, each with its own brief moment of promise. Researchers have pointed to unusual tracks in ancient mica or strange signals in cosmic ray data, events that could not be immediately explained away. Each one generated a surge of excitement and intense scrutiny, but in every single case, further investigation revealed a more mundane explanation. A trace of contamination in a sample, an unexpected fluctuation in the equipment, or the passage of a heavy but ordinary atomic nucleus could mimic the expected signal. These episodes are not failures of science, they are science in action. They reveal a process built not on triumphant announcements, but on ruthless skepticism and the unwavering demand for reproducibility. A single event, no matter how perfect, is not enough. For a discovery to be accepted, it must be confirmed independently and repeatedly. This rigorous process is what separates a fleeting anomaly from a fundamental truth. These false alarms teach a profound lesson about the human side of this cosmic quest. They are stories of brilliant minds allowing themselves a moment of hope, of the crushing disappointment that follows, and the sheer perseverance required to continue the search despite decades of silence and dead ends. Every null result, every explained-away signal tightens the constraints. It tells us where monopoles are not and what they cannot be, slowly narrowing the possibilities and sharpening the hunt. This relentless cycle of hope and disappointment is the engine that drives science forward, forcing ever more creative and careful experiments in an unyielding pursuit of a truth that remains, for now, just out of reach. This relentless search is driven by more than pure curiosity. The discovery of a single magnetic monopole would not just be a scientific triumph, it would ignite a technological revolution on a scale we can barely comprehend. Think of electricity before we understood how to harness it, a fascinating natural phenomenon waiting for a Franklin or an Edison to unlock its potential. Magnetic monopoles represent a similar frontier, a new fundamental force of nature waiting for its inventors. The first and most immediate impact would be in the world of data. Our entire digital civilization runs on the ability to store and read information, and magnetic monopoles could rewrite the rules completely. Modern hard drives work by flipping tiny magnetic domains on a spinning platter, a process that is reaching its physical limits. But a monopole, with its singular north or south charge, is the smallest possible unit of magnetism. It is the ultimate binary digit. A storage device built with monopoles could pack data into a density that makes our current technology look prehistoric. We are talking about computers with unimaginable memory and processing power, fitting the entire Library of Congress into a device the size of a sugar cube. This is not just an incremental improvement, it is a quantum leap into a new era of computing. Beyond data, the energy implications are even more staggering. Our current electrical grids are based on moving electrons, which always encounter resistance, wasting energy as heat. But a flow of magnetic monopoles would be something entirely new, a magnetic current. This could lead to the development of a monopole battery, a device that stores pure magnetic charge, because monopoles would not interact with matter in the same way electrons do. Such a power source could be incredibly efficient and potentially hold immense amounts of energy in a very small space. It could power a city for a week or a car for a lifetime, all from a device you could hold in your hand. The very way we generate power could be transformed. Monopoles could act as perfect catalysts for novel energy conversion, turning heat or light directly into usable magnetic power with near-perfect efficiency. Imagine a solar panel not that generates a trickle of electricity, but that produces a powerful, direct magnetic current. These are not just better versions of what we have, they are foundations for technologies that do not yet exist, built on a new pillar of physics. Finding the first monopole would be like giving humanity a new set of tools for manipulating reality itself, opening doors to a future we are only beginning to dream of. That potential for a monopole battery is just the beginning. The true revolution lies in reimagining the very machines that power our world. Think of an electric motor or generator today. They work by spinning magnets past coils of wire, inducing an electrical current or vice versa. This process is fundamentally messy. There is friction, heat loss, and resistance at every turn, robbing the system of efficiency. Now replace the messy flow of electrons with a pure, direct current of magnetic charge. A motor powered by monopoles would experience almost no energy loss. It would be a device of perfect, silent efficiency, converting stored magnetic energy directly into motion without the wasteful byproducts of heat and sound. Generators could become so efficient they could harvest ambient magnetic energy from the environment itself, tapping into a power source we currently cannot even perceive. This is not just an upgrade, it is the difference between a water wheel and a modern turbine. It is a fundamental shift in engineering principle. This leap enables a sci-fi staple to become reality: magnetic levitation. Today's maglev trains are marvels, but they are still complex systems that require powerful electromagnets and precise control systems to achieve lift. They are fighting against the dipole nature of ordinary magnets, but a material or device that could control a flux of monopoles would grant us mastery over magnetic fields in a way that is currently pure fantasy. We could create truly stable, persistent magnetic fields that require zero energy to maintain. This is the key to frictionless transportation, not just on guide rails, but everywhere. Imagine vehicles that hover effortlessly above any surface, silently gliding through cities without touching the ground. The energy savings would be monumental, eliminating the massive drag that currently dominates transportation costs. And the applications would soar literally into the heavens. Monopole-based propulsion could offer a new, highly efficient method for pushing spacecraft. Instead of burning vast quantities of chemical fuel, a ship could generate a powerful, directional magnetic field, pushing against the magnetic fabric of space itself or against planetary magnetic fields for a continuous, efficient thrust. This could slash travel times within our solar system, turning a journey to Mars from a multi-month expedition into a routine voyage. These are not mere improvements on our current technology. They represent the birth of an entirely new branch of engineering, built on a pillar of physics we have yet to confirm. This is why the decades-long, silent hunt for the magnetic monopole is so much more than an academic puzzle. It is a search for the cornerstone of our next civilization, a single particle holding the key to a future of limitless, clean energy and technological wonders we can only begin to imagine. But what if the silence is the final answer? The continued absence of magnetic monopoles carries a profound and unsettling weight. For decades, their discovery has been seen as an inevitability, a necessary validation of our most elegant theories. If they are truly not there, the foundations of modern physics would face a tremor unlike any other. Grand unified theories, which so beautifully predict a monopole-saturated early universe, would be dealt a devastating blow. We would be forced to ask a painful question. Is our pursuit of a single, unified description of reality fundamentally flawed? Have we been following a beautiful mathematical path that simply does not correspond to the universe we inhabit? The implications ripple outward, even touching our saving grace, the theory of inflation. While inflation elegantly explains why we do not see monopoles everywhere, its own credibility is partly tied to solving the problem they created. If the monopoles were never there in the first place, one of inflation's primary reasons for existing evaporates, we are left with a cosmic sleight of hand that fixed a problem that may not have been real. This is not a failure of science, but its most demanding and honest expression. The universe is under no obligation to conform to our sense of elegance or our desire for perfect symmetry. The stubborn emptiness we observe forces a radical humility upon us. It pushes us to imagine entirely new principles, to consider that the fundamental forces may not unify in the way we expect, or that the birth of the cosmos followed a script we have not yet conceived. The missing monopole becomes a ghost that haunts our textbooks, a constant reminder that the greatest discoveries often come not from finding what we seek, but from being forced to rethink everything we thought we knew. This stubborn emptiness has forced physicists to become cosmic architects, designing entirely new blueprints for reality. When a problem refuses to be solved, you must question the very foundations it stands on. The monopole problem is exactly that kind of catalyst, pushing scientists to imagine origins for the universe that bypass the need for inflation altogether. One such radical idea is the ekpyrotic universe. Forget a single hot Big Bang from a singular point. This theory paints a picture of a cyclical cosmos, where our universe is born from a collision between two higher dimensional worlds, like two sheets of reality brushing past each other in a vast, unseen bulk. This collision converts kinetic energy into the matter and radiation we see, but it does so without ever passing through a phase of extreme, unified symmetry. Without that specific hot, symmetric beginning, the topological knots that become magnetic monopoles simply never form. It is a creation story that elegantly sidesteps the entire problem, like building a house without ever creating the kind of rubble that would clutter the yard. Another set of theories, the cyclic models, take this even further. They propose an eternal, repeating cycle of cosmic death and rebirth. The universe expands, but instead of fading into cold emptiness, a mysterious dark energy field decays, allowing gravity to pull everything back together in a big crunch. This collapse does not end in a singularity, but rather triggers a bounce, a transformation into a new Big Bang. In these models, each cycle is a fresh start, and the conditions that mass-produce monopoles are carefully avoided. The cosmos is like a phoenix, continually rising from its own ashes, but each new incarnation is cleansed of the specific relics that plagued its predecessor. These are not minor tweaks to the standard story. They are complete paradigm shifts born from the need to explain a profound absence. The missing monopole is the ghost at the feast of cosmology, a spectral guest whose non-appearance is so troubling it compels us to rethink the entire party. It forces the question, is our universe a one-time explosive event, or is it part of an eternal, breathing rhythm we are only beginning to perceive? Even our most radical reimaginings of the cosmos may not go far enough. To truly confront the monopole, we must venture into the realm of string theory, a framework where the very idea of a particle is transformed. Here, the fundamental constituents of reality are not zero-dimensional points, but incredibly tiny, vibrating loops of energy. In this multidimensional tapestry, a magnetic monopole is no longer just a solitary dot of north or south charge. It can manifest as a higher dimensional object, a membrane or D-brane, that exists within the hidden, compacted dimensions string theory requires. Imagine our familiar three-dimensional space as a vast, thin sheet. A D-brane could be like a one-dimensional string stuck to that sheet, or a two-dimensional wall slicing through it. A magnetic monopole in this picture is not a point you can pin down, but a stable, soliton-like knot of energy within this richer geometry. This perspective does something remarkable. It makes the existence of such entities almost inevitable within the math. The theory's need for consistency and its intricate symmetries naturally give rise to objects that carry the exact properties of a magnetic monopole. They are not awkward additions, but fundamental features of the theoretical landscape. This also provides a compelling reason for their profound scarcity. If monopoles are these extended, massive objects tied to the geometry of hidden dimensions, their production in the early universe becomes a much more delicate and rarefied event. They would not be forged in the same overwhelming numbers that simple grand unified theories suggest. Their creation might require specific, fine-tuned conditions, making them cosmic rarities rather than common dust. String theory, in its breathtaking ambition, reframes the entire problem. The question shifts from why we do not see endless monopoles to whether the specific vibrational patterns and topological structures of our particular universe allowed only a precious few of these exotic entities to ever form. It connects the ghostly absence in our experiments directly to the deepest, most hidden architecture of reality itself. This line of reasoning leads us to a profound and controversial question about our own place in the cosmos. What if the reason we do not see magnetic monopoles is that we are here to look for them? This is the essence of the anthropic principle, a philosophical argument that turns the mystery on its head. The logic is starkly simple. A universe teeming with monopoles, as predicted by naive grand unified theories, would have been a cosmic disaster. The gravitational influence of all that missing mass would have caused the early universe to collapse back on itself in a fraction of a second. There would have been no time for galaxies to coalesce, for stars to ignite, and for planets to form. Life and the physicists who ponder such questions would never have arisen. Therefore, the argument goes, it is no surprise that we find ourselves in a universe that appears empty of monopoles. We could not possibly exist in any other kind. This is not an explanation of how the monopoles vanished, but why we must observe their absence. It is a form of cosmic selection, where the very conditions that allow for observers like us naturally filter out the realities we are capable of witnessing. Proponents see it as a sobering dose of reality, a reminder that our observations are not unbiased. We are not random spectators of the cosmos, we are products of it, and our existence imposes strict limits on what the universe can be like. We are, in a sense, fishing in a very particular pond and wondering why we only catch certain types of fish. The pond we are fishing in is the only one that could have produced us. Critics, however, find this reasoning deeply unsatisfying, even unscientific. They argue that the anthropic principle risks explaining away a major problem by invoking a tautology, a circular logic that says we see what we see because we are here to see it. It does not provide a physical mechanism for the monopole's absence. It simply states that our existence is incompatible with their presence. For many, this feels like giving up on the search for a real, testable cause, retreating into philosophy when physics fails. Does this principle shut down further inquiry, or does it rightly guide us toward the kinds of universes that are possible? The debate forces us to confront the limits of scientific explanation itself. Are we uncovering the universe's fundamental laws, or are we merely cataloging the necessary conditions for our own existence? The silent, empty cosmos offers no easy answer, only the haunting possibility that the greatest mysteries are intertwined with the mere fact that we are here to ponder them. The search for the monopole has not been confined to sterile laboratories and deep underground caverns. This elusive particle has escaped the pages of physics journals and ignited the imaginations of storytellers, becoming a secret weapon for science fiction. In countless novels, films, and games, the magnetic monopole is rarely just a particle, it is a key. It unlocks impossible technologies, powers starships across gulfs of space, or becomes the ultimate superweapon that can rewrite the rules of engagement. These fictional monopoles are plot devices of pure potential, representing a future where humanity has finally cracked the code of magnetic charge and harnessed its power. A writer does not need to understand the intricacies of grand unified theories to grasp the narrative power of a fundamental, singular force. The concept is intuitively brilliant, a north without a south, a broken symmetry that promises control over one of nature's most pervasive yet tamed forces. This cultural adoption performs a subtle magic. It acts as a bridge. The dense mathematical certainty of Dirac's equations is translated into the visceral thrill of a starship's engine humming with monopole-derived power. An audience that might never read a paper on topological defects can understand the drama of a quest for a rare, cosmic substance that could save or destroy a civilization. It makes the esoteric tangible, wrapping a complex scientific mystery in the accessible cloak of adventure and human drama. These stories are more than just entertainment, they are a form of public dreaming. They take the dry prediction of a missing particle and give it color, sound, and consequence, inspiring a new generation to look at the night sky and wonder what other keys to the future might be hiding in the void. That stubborn silence from the cosmos is not a signal to stop looking, it is a reason to look harder. The hunt for the magnetic monopole is accelerating, evolving with proposals for experiments that dwarf our current efforts. Imagine launching a detector beyond Earth's magnetic field, a silent observatory in the deep space between planets, free from the background noise of our world. Such a space-based detector could listen for the faintest whisper of a monopole passing through the solar system with a clarity impossible to achieve on the ground. Back on Earth, the blueprints for next-generation particle accelerators are already being drawn. These machines would be vastly more powerful than the Large Hadron Collider, colliding particles with such immense energy that they could probe realms of physics currently beyond our reach, perhaps finally crossing the threshold needed to create a monopole from the vacuum of empty space. Each new proposal is a testament to our refusal to let the mystery stand. But this is not a story of failure. Every empty result, every experiment that comes up blank is a crucial piece of data. It is like meticulously searching a vast, dark room with a flashlight. With each sweep, you do not find what you are looking for, but you learn more about the room's dimensions and where the object cannot be. Scientists use these null results to set stricter and stricter limits, ruling out entire classes of theories and forcing the possible properties of the monopole into a narrower, more precise box. This relentless, decades-long pursuit is far more than a technical challenge. It is a pure expression of the scientific spirit. It is the drive to answer a fundamental question about the fabric of reality, to complete a symmetry that seems too beautiful to be wrong, no matter how many years or how many resources it takes. The search itself, with its blend of profound hope and disciplined patience, defines our quest to understand the universe we call home. This entire quest feels deeply personal. You spend your days living inside the mathematics, a world of such profound symmetry and elegance that the existence of magnetic monopoles feels inevitable. They are not just particles, they are consequences. When the equations point so clearly to something, you develop a kind of faith in its reality. My motivation is simple. I want to see that the universe agrees with its own underlying beauty. The frustration is not in being wrong, it is in the silence. You check your work, you rederive the conditions, and the answer always comes back the same. The early cosmos should be filled with them, and then you look at the blank slate of experimental data year after year, and that silence becomes a constant, quiet companion. A typical day is a cycle of intense focus and shared speculation. I might spend the morning at a chalkboard, tracing through the implications of a grand unified theory, mapping out the phase transitions of the infant universe. The math tells a story of a hot, symmetric beginning that breaks, and in that breaking, topological defects like monopoles are the inevitable cracks in the cosmic ice. It is a compelling narrative written in the language of group theory and differential geometry. Then, in the afternoon, I'll be with colleagues debating over coffee. We are not just talking about abstract ideas, we are problem solving. Could the monopoles be far more massive than we think, placing them forever beyond our colliders? Could they have decayed through some mechanism we haven't considered? These conversations are a lifeline, a reminder that this is a human endeavor, a collective grappling with a mystery. There is always a thread of hope, a palpable anticipation every time a new paper from an experiment like Monopoles is published. You open it with a mix of excitement and dread, scanning for that one graph, that one data point that could validate decades of theoretical work. You are waiting for a signal from the universe, a nod that says you were on the right path all along. That hope is what gets you back to the chalkboard the next day, ready to trace the elegant lines of a theory that, against all evidence, still feels true. The theoretical elegance is one thing, but the reality of the hunt is something else entirely. My world is not made of chalkboards and equations, but of wires, liquid helium, and an endless war against noise. I am an experimentalist, and my job is to build a trap for a ghost. The challenge begins with the detector itself. We are trying to sense a particle that might only pass through a square meter of Earth's surface once in a century, if that. Our instruments have to be so sensitive they border on the impossible. Just the vibrations from a truck driving a mile away or a subtle shift in the Earth's magnetic field can create a signal that perfectly mimics what we are looking for. We build our experiments deep underground, shielded by tons of rock, and cool our detectors to within a fraction of a degree of absolute zero, just to quiet the frantic jiggling of atoms themselves. It is a constant battle to create a perfect, silent room in a universe that is never truly quiet. Then comes the data, a relentless river of numbers. For every single run of an experiment, we might collect petabytes of information, a mountain of digital static. My team and I spend months, sometimes years, sifting through it all. We are looking for that 1 in a billion spike, that unique pattern that cannot be explained by any known particle or any earthly interference. It is a painstaking process of elimination, ruling out cosmic rays, radioactive decay from the very rocks around us, even subtle electrical faults in our own equipment. You have to be part scientist and part detective, chasing down every possible false lead until you are left with only the truly inexplicable, and that is where the thrill lies. It is the thought that one day, amidst that endless sea of noise, I might be the first person to see a signal that no one in the history of humanity has ever witnessed. To look at a screen and see a curve that is so perfect, so clean, that you know in that instant you are staring at a magnetic monopole. It is a humbling, terrifying, and electrifying possibility. That moment would not just be a personal triumph, it would be a gift to every physicist, past and present, who ever dared to believe the universe was that symmetrical, that beautiful. It is a long shot, but someone has to be ready to catch it. This global hunt for a ghost particle comes with a real price tag. While no single monopole search commands the colossal budget of the Large Hadron Collider, the collective investment is immense. Consider the decades of work by specialized research groups at universities and national laboratories worldwide. Their funding pays for advanced materials, from ultra-pure aluminum blocks to acres of plastic nuclear track detectors. It covers the staggering energy costs of running supercooled experiments near absolute zero for years on end, and it supports the salaries of brilliant minds who could be applying their talents to more immediately profitable ventures. When you add the theoretical side, the physicists developing grand unified theories and cosmological models, the total societal investment over the years reaches into the hundreds of millions, if not billions, of dollars. So why spend so much on a pursuit that has, for half a century, yielded nothing but silence? The justification lies in a simple, powerful truth. The history of fundamental science is a graveyard of predictions that underestimated the value of pure curiosity. When James Clerk Maxwell unified electricity and magnetism in the 1800s, he was not trying to invent the radio or the electric power grid. He was driven by a desire to understand the deep laws of nature. His abstract equations, born from pure inquiry, ultimately laid the entire foundation for our modern electronic world. The search for the monopole is no different. We are not funding a treasure hunt for a single particle. We are investing in the entire ecosystem of discovery that surrounds it. The extreme technologies developed to hunt for monopoles, like superconductors and exquisitely sensitive magnetic sensors, have already found their way into medical MRI machines, mineral exploration, and even quantum computers. The pursuit of this one cosmic answer forces us to invent new tools, and those tools inevitably unlock capabilities we never knew we needed. This is not a cost, it is a seed planted in the soil of the future. The potential technological payoff is only half the story. The deeper return on investment is cultural and philosophical. Humanity is a species defined by its need to ask why. To look at the stars and question the fundamental rules of existence is a core part of what makes us human. Channeling resources into this grandest of puzzles is an affirmation of that spirit. It tells the next generation that understanding the universe is a worthy endeavor in its own right, that we value knowledge for its own profound sake. The money spent is a statement that our civilization is about more than just immediate consumption and short-term gains. It is about expanding the horizon of human understanding for all who come after us. The discovery of a monopole would be a monumental event, but the search itself, with all its costs and frustrations, is already a testament to our highest aspirations. The ghost haunting our experiments might be the very thing holding the cosmos together. We have chased the magnetic monopole for decades, finding only silence. But what if that silence is filled with something we already know is there? This line of thinking leads us to one of the most audacious and speculative ideas in modern physics, a potential bridge between two profound mysteries. Could magnetic monopoles be a constituent of dark matter? Think about the properties of dark matter. It must be stable, or it would have decayed away over the universe's lifetime. It must be massive to provide the gravitational glue for galaxies, and it must interact only very weakly, if at all, with light and ordinary matter, which is why it is completely invisible to our telescopes. Now consider a particular class of magnetic monopole predicted by some grand unified theories. These are not the light, fleeting particles we might hope to create in a collider. They are behemoths, incredibly massive, perhaps as heavy as a bacterium compressed into a single subatomic point. Such an object would be inherently stable, a topological knot in spacetime that cannot simply unravel. And because its primary interaction is magnetic, and magnetic fields are screened by ordinary matter, it would pass through the Earth and our detectors as if they were not even there, leaving only the faintest, most elusive trace. This is a perfect match for the description of a dark matter particle. The implications are staggering. Every time we look at a galaxy and see stars orbiting too fast, held in place by the gravity of unseen mass, we might be indirectly observing the collective pull of countless magnetic monopoles. The very particles we have been hunting in vain could be flowing through you and me at this very moment, constituting the invisible skeleton of the cosmic web. Solving the monopole problem would not just complete a symmetry in physics, it would suddenly illuminate 85% of the matter in the universe. This is the ultimate two-for-one deal, where finding one ghost would reveal the identity of another, larger phantom that has perplexed us for nearly a century. The search for the monopole transforms from a quest for a missing particle into a hunt for the hidden architecture of reality itself. This very struggle, this decades-long dance between elegant theory and stubborn reality, makes the monopole problem a perfect classroom. It is a masterclass in the scientific method in action, far removed from the sanitized version often found in textbooks. For a student, science can sometimes feel like a collection of settled facts, a dusty archive of answers. But the story of the missing monopole is different. It begins with a beautiful idea, a mathematical symmetry so compelling it feels like it must be true. Paul Dirac's work and the later grand unified theories are pinnacles of human reasoning, predicting a universe that should be overflowing with these particles. This is the first crucial lesson. Science starts not with random guessing, but with logical, often beautiful, predictions derived from our best models of how the world works. Then comes the confrontation with nature itself. The next step is not to dismiss the data that does not fit, but to embrace it. The relentless global search, the empty results from deep mines and ancient rocks, the silent superconducting loops, this is the evidence that holds a theory accountable. It forces a moment of intellectual crisis. Do we abandon the beautiful theory, or does the theory need to be saved from its own success? This is where the process becomes truly dynamic. The proposal of cosmic inflation is a brilliant example of this self-correction. It was not a rejection of the earlier theories, but a creative addition, a new chapter that preserved the core ideas while explaining why our observations do not match the initial naive prediction. It shows science as a living, breathing process of problem solving, where dead ends are not failures, but invitations to think more deeply. A student following this story does not just learn about magnetic monopoles, they learn how science really works. They see that it is a cycle of prediction, experimentation, crisis, and innovation. It is a human story of brilliant minds being humbled by the universe and then rising to the challenge with even more brilliant ideas. This single cosmic mystery encapsulates the entire spirit of inquiry, teaching the next generation that the most exciting part of science is not the answer in the back of the book, but the thrilling, unanswered question that keeps us all searching. The next decade of this search will be defined by a new generation of tools, machines that listen for whispers we were once deaf to. Quantum sensors represent a revolutionary leap in this pursuit. These are not merely better versions of today's equipment, they are devices that operate on the bizarre principles of quantum mechanics itself. Imagine a magnetometer so sensitive it could detect the magnetic field of a single electron from across a room. By harnessing the quantum states of individual atoms or delicate superconductors, these sensors can achieve a level of precision that borders on magic. Deployed in ultra-quiet environments, perhaps deep in space or at the silent bottom of the ocean, such a sensor could finally pick up the faint, unique magnetic signature of a monopole drifting silently through the solar system, a ghost finally heard by a listener with perfect ears. On the energy frontier, the plans for future particle colliders are already being drafted. These would be machines of almost unimaginable scale, accelerating particles in rings that could encircle entire cities or in linear paths stretching for dozens of miles. Their goal is to reach energy levels that mirror the first trillionth of a second after the Big Bang, a realm where the symmetry of the primordial forces was absolute. If a magnetic monopole is a knot tied in the fabric of space-time during that epoch, these colliders would not just be probing for it, they would be attempting to reweave the fabric itself, shocking the vacuum into tying that knot once more right before our eyes. And our view of the cosmos is also expanding. The next generation of space telescopes and radio observatories will map the universe with unprecedented detail. studying the magnetic fields of distant galaxies and galaxy clusters. They will be looking for subtle, anomalous effects, a strange dimming or strengthening of these vast magnetic structures that could only be explained by a sparse population of monopoles weaving their way through the cosmic web. This turns the entire universe into a detector, using the largest structures we know to find the smallest of missing pieces. So, could the discovery happen tomorrow? It is a tantalizing possibility. A lone researcher could right now be examining a piece of ancient mica and find a trail that defies all conventional explanation. A data spike in a superconducting loop buried under a mountain could, this very night, trace the perfect, unmistakable curve. The nature of this quest means the answer could come at any moment, a sudden event that rewrites physics in an instant. Yet, the sheer scale of the cosmos and the profound silence so far suggest we may be in for a much longer hunt, a centennial project that demands patience as much as brilliance. This is the thrilling uncertainty of living on a scientific frontier. We are surrounded by the hum of experiments that grow more powerful each year, all aimed at a single profound goal. The next chapter of this story is being written in the blueprints for new machines and the quiet dedication of those who refuse to stop looking. Ultimately, the magnetic monopole stands as one of science's most profound and persistent riddles. Its absence is not a void but a force, a ghost that has challenged our grandest theories, inspired cosmic solutions like inflation, and driven the creation of technologies sensitive enough to hear the universe's faintest whispers. This search is far more than a particle hunt. It is a mirror reflecting our deepest desire to find order and symmetry in the cosmos. Whether these particles are cosmic phantoms hiding in the vast dark, relics stretched to near nothingness by an explosive infancy, or simply a beautiful idea that the universe chose to ignore, their story pushes the very frontiers of what we can know. This narrative is still being written, its final chapter waiting in the data of a future experiment or the insight of a new mind. So the next time you hold a simple magnet, remember the cosmic mystery it represents and keep looking up. Who knows, the missing piece of the puzzle might just reveal itself to you. What do you think is out there? Share your own theories in the comments below.